Sometimes a glacier is compared to a conveyor belt. No matter whether the front of a glacier or ice sheet is advancing, retreating, or stationary, it is constantly moving sediment forward and dropping it at its terminus. This is a useful analogy when considering end and ground moraines. An end moraine is a ridge of till that forms at the terminus of a glacier. End moraines are characteristic of ice sheets and valley glaciers alike. These relatively common landforms are deposited when a state of equilibrium is attained between ablation and ice accumulation. That is, the end moraine forms when the ice is melting and evaporating near the end of the glacier at a rate equal to the forward advance of the glacier from its region of nourishment. Although the terminus of the glacier is stationary, the ice continues to flow forward, delivering a continuous supply of sediment in the same way a conveyor belt delivers goods to the end of a production line. As the ice melts, the till is dropped, and the end moraine grows. The longer the ice front remains stable, with ablation and accumulation in balance, the larger the ridge of till will become. Eventually, ablation exceeds nourishment. At this point, the front of the glacier begins to recede in the direction from which it originally advanced. However, as the ice front retreats, the conveyor belt action of the glacier continues to provide fresh supplies of sediment to the terminus. In this manner, a large quantity of till is deposited as the ice melts away, creating a rock-strewn, undulating plain. This gently rolling layer of till deposited as the ice front recedes is termed ground moraine. It has a leveling effect, filling in low spots and clogging old stream channels, often leading to a derangement of the existing drainage system. In areas where this layer of till is still relatively fresh, such as the northern Great Lakes region, poorly drained swampy lands are quite common. Periodically, a glacier will retreat to a point where ablation and nourishment once again balance. When this happens, the ice front stabilizes, and a new end moraine forms. The pattern of end moraine formation and ground moraine deposition may be repeated many times before the glacier has completely vanished. Such a pattern is illustrated in Figure 18.26. The very first end moraine to form signifies the farthest advance of the glacier and is called the terminal end moraine. End moraines that form as the ice front occasionally stabilizes during retreat are termed recessional end moraines. Terminal and recessional moraines are essentially alike, the only difference between them is their relative positions. Smart Figure 18.26 End moraines of the Great Lakes region. End moraines deposited during the most recent, Wisconsin stage are the most prominent. Animation. Glacial processes. End moraines deposited by the most recent stage of Ice Age glaciation are prominent features in many parts of the U.S. Midwest and Northeast. In Wisconsin, the wooded, hilly terrain of the Kettle Moraine near Milwaukee is a particularly picturesque example. A well-known example in the Northeast is Long Island. This linear strip of glacial sediment extending northeastward from New York City is part of an end moraine complex that stretches from eastern Pennsylvania to Cape Cod, Massachusetts, Figure 18.27. Smart Figure 18.272 Significant end moraines in the Northeast. The Ronkonkoma Moraine, deposited about 20,000 years ago, extends through central Long Island, Martha's Vineyard, and Nantucket. The Harbor Hill Moraine formed about 14,000 years ago and extends along the north shore of Long Island, through southern Rhode Island and Cape Cod. A portion of the mobile field trip explores the glacial origins of Cape Cod. Mobile field trip. A trip to Cape Cod. Figure 18.28 represents, your browser doesn't support.
Welcome aboard, and welcome to Cape Cod. The Cape's a spur that juts from mainland Massachusetts out into the Atlantic Ocean. Down there you can see lakes called kettles, as well as spits and harbors. On this field trip, we'll try to understand how the Cape and nearby islands were originally formed. These waters are rough in winter. We'll see how storms constantly mold the white sand beaches. And we'll look at the different roles that wind and water play in the evolution of Cape Cod. Geologists call America's east coast a passive margin, but historians think of the shoreline as anything but passive. When Esteban Gomez sailed here from Spain in 1525, he named Nantucket Island Cape Shoals. Shoals are shallow sandbars that lie just off a coastline. At Cape Cod they've sunk thousands of ships. What makes this coast so treacherous? Technically and geologically, the entire east coast is a passive continental margin because halfway to Europe, the Atlantic Ocean seafloor is being pulled apart across a mid-ocean ridge. Unlike the west coast with its active margin, subduction isn't pushing the east coast up into cliffs. A passive margin is, well, passive. It just sits there. There aren't many earthquakes or volcanoes. Consequently, the two shorelines look quite different. Here on the east coast, lazy rivers flow down to the shoreline where they dump sand to form long, beautiful beaches. Beyond the beaches lies the continental shelf, that gently sloping submerged portion of the continent, which only gradually becomes deeper offshore. Cape Cod sticks out from the mainland like a waving arm bent at the elbow. Unlike most of New England, the Cape isn't bedrock. It's made of loosely consolidated sediments. 2 islands, Nantucket and Martha's Vineyard, lie just south of Cape Cod. Their low bluffs are composed of poorly sorted boulders, cobbles, gravel, and sand, classic glacial till. As the Ice Age waned, this till was deposited as an end moraine, marking the great Laurentide ice sheet's maximum advance southward from the Arctic. The midriff of Cape Cod itself is also a moraine, but it's considered recessional, deposited a little ways back from the terminus during glacial retreat 18,000 years ago. As the glaciers disappeared, they left behind calling cards, unlikely gigantic boulders called erratics like Doan Rock near Nauset Bay, too large to have been transported over this flat land by anything but ice. Elsewhere, large blocks of ice were stranded after their parent glaciers retreated. When the blocks melted, their depressions filled with fresh water, forming lakes that are now called kettles. Oddest of all are shallow valleys scattered across Cape Cod that don't seem to make sense. Inconsequential streams meander across their flat bottoms. The valleys are relics of the days of glacial outwash plains. The outer beach stretches unbroken from Nauset Harbor north to Provincetown. Bluffs of glacial till rise 180 feet above its midsection. This beach bears the full brunt of nor'easter storms that sweep in from the North Atlantic every winter. These storms periodically strip the beach and gnaw bluffs back 3 feet a year and more in places. The beaches may shrink during a storm, but are quickly replenished by sands from the eroding bluffs. Every time a wave, large or small, breaks against Cape Cod, sand is swept up from the water's edge and then rolls back down with the retreating wave. During storms, some sand is carried out to sea, forming those treacherous shoals that lie just below the water's surface. But a lot of sand remains close to shore. If it weren't for beach drift and longshore currents that brush against Cape Cod, grains would endlessly wash up the beach and just roll back down in the same place with each breaking wave. Instead, beach drift transports sand laterally along the beach, the path describing a sawtooth pattern that incrementally moves material in the direction of the current. The bluffs above Outer Beach stretch 16 miles north from Nauset Harbor. Beyond that, Cape Cod exists because longshore currents steadily pump sand northward from the bluffs, building a thin peninsula called a spit. Near Provincetown, some grains are lifted by the wind beyond the reach of waves to form sand dunes. Henry Beston, after a winter spent living on the beach near Nauset, wrote, "The sand here has a life of its own, even if it's only a life borrowed from the wind." From Nauset Harbor south, sand accumulates as a string of spits and migrating barrier islands from North Beach to Monomoy. These features are dynamic, influenced season to season by those nor'easter storms. Barrier islands provide an offshore buffer against which storm waves break before reaching the true coast. Large storms will sometimes breach the islands, rearranging them until more sand arrives to fill the gaps. Do you think this would be a good place to build that idyllic cottage facing out to sea? Cape Cod, above all, is a dynamic landscape. Since it was created by glaciers at the end of the most recent ice age, the Cape has constantly been adjusting to the whims of sediment supply and demand. Times are changing, though. Sea level is rising as our climate warms. Erosion, already a threat to homeowners who overlook the bluffs, is likely to accelerate. The future of those homes is measured in months rather than years. Indeed, the beach, bluffs, and even Cape Cod itself are likely to be gone in a few thousand years. What did you learn? Which geologic agent has not been active in the creation of Cape Cod? Glaciers, turbidity currents, wind? Glaciers and wind have been active in the creation of Cape Cod, but turbidity currents which scour deeper parts of the ocean floor have not. Which of these rocks could have been deposited in an environment similar to the coast off Cape Cod?